Hello to anyone who's watching. My name is Mech Proj2, and for my mechanics project, I chose to analyze the three-body gravitational system. So the three-body gravitational system is basically just a system of three bodies with mass, all under the effect of gravitational forces due to each other. So all the forces are conservative, central, and internal. So this means also that momentum is conserved, which is important. Also, most notably, the system is also chaotic, which is kind of the whole point of the project. So a little historical background to the three-body problem. It dates as far back as 1687 in Isaac Newton's Philosophiae Naturalis Principia Mathematica, which was his first notable book, where he kind of lays out all of his laws, and he does apply his laws to the three-body problem, and then tries to apply the three-body problem to the Sun, Earth, Moon system. This naturally brings us to solutions to the problem. As it stands, and probably will always stand, there are no general solutions to the problem because it is chaotic. So there's not a singular finite solution or equation that describes the motion of these bodies. Although there are many particular or special solutions like the figure-8 solution, and there are actually currently over 2,000 particular solutions, which are all technically different, but a lot of them are somewhat similar. And some of the other applications of the three-body problem extend to like the Coulomb force. So, of course, the Coulomb force is also central and can be attractive. So, of course, the three-body problem applies to the Coulomb force as well. And thus it can be used to model like the helium atom. So the electrons orbiting the negatively charged electrons orbiting the positively charged nucleus. So now to get into the actual logistics and math of the problem. The equation of force on a given body is just the standard law of gravitation, Newton's law of gravitation. It's summed over the all of the planets excluding the given one. So if you're talking about planet 1, then you just calculate the forces due to planet 2 to n, excluding 1 so that you don't double count, which is shown here. And then the acceleration is, of course, just the force divided by the mass. Now, what I brought up earlier was that momentum is conserved, which means that total momentum is constant. Now, conserved momentum implies constant velocity, considering mass is also, of course, constant, just given the nature of the problem. So to prove that momentum is conserved, one way of doing that is proving that the velocity is constant, or showing that the velocity is constant. And so by these two equations here, we can obtain our total velocity of the system. And then if it turns out to be constant, then we know that momentum is conserved. So now to get into the code, to start off with importing our standard libraries for these kind of problems, matplotlib and numpy. I then defined a class body just to kind of collect all of the values into one spot for each planet so that I didn't have to have a bunch of arrays and stuff like that, which I actually did end up having a bunch of arrays, but for different reasons. So each body object will just have a mass, which will be a floating point number, and then position and velocity, which will both respectively be NumPy three-element arrays. And then I define some functions, one that calculates the magnitude of a vector, the unit vector of a vector, the center of mass of given three planetary bodies, total momentum of the bodies, and the acceleration of the bodies. So then I need to define the physical constants. The only ones here are the gravitational force, or the gravitational constant, sorry, and initial time and time step. There's really no other forces or need for any more constants here. So then this is where I create each planet object, and then I create an object for the center of mass, setting its position equal to the center of mass of the system, and then its velocity to the total momentum divided by the total mass, which, as we saw above, was the total velocity. And I set the mass equal to 0 because we don't care about any forces acting on that, so it's fine to just leave it at 0. And then I create a bunch of lists to store, different quantities. And then I loop over to 20 simulated seconds, updating accelerations, velocities, positions, and then incrementing time. Also momentum, or at least total momentum of the system. And then convert those lists to NumPy arrays. So now that we have all of these values, we can start analyzing our problem. So the first thing I do is just plot the positions of each planet and the center of mass. So we can see that here. We can see here too the legend, planet 1, planet 2, planet 3 being blue, red, and green respectively. And then the center of mass is the black line. So we can obviously see that the positions are pretty chaotic. They're all over the place. They don't really follow a pattern that can easily be modeled with just a standard equation. But we do see that the center of mass seems to have a constant velocity, not be accelerating, just following a straight line. And we'll see in a second that that is in fact true. So now I'm going to kind of dive into the conservation of momentum aspect. So here I'm first going to calculate the magnitude of the position and velocity of the center of mass, so it's going to kind of look like the velocity, it's going to look like the position is not a linear function, but it just looks like that because it's the magnitude of it. So we can see here, it looks like position is not following a linear path, but it is. It's just because it's the magnitude. But we do see that the magnitude of the velocity is constant all the way across the board. So next, I'll go into the components of the velocity, and then we'll really be able to see that the velocity or the position is linear. So now we look at the x component, so we can see here that the x position is linear and with a negative slope. We do see that the x velocity is constant, and we can again see that for the y component as well. And to finish off, I did make a little animation using GlowScript. It's the same code, same initial values. It's just that we'll be able to see the animation of the bodies. So here we go. So we can see our different planets. We get to planet 1, 2, and 3. And then this is our center of mass. So I'll just let that play out for the 20 simulated seconds. All right, so those are the 20 seconds up, and we can see our plot here, which looks just like the one we got over here. So that checks out. And yeah, we see the center mass is following a straight line. System is chaotic. So that's a little animation. And thank you very much for watching. And